Well, good morning. We're going to try this out, see how this goes. I've got the ability to show you my tablet here. I've got Canvas there. I've got Notebook. I've got my textbook here. Let's try to, if we can, let's review for exam 2 real quick. That's kind of a nice, simple thing that we can do. See how this works. I've got, as you can see here, I've got a camera set up where I can basically a document camera, and let's just try this out. Let's see how this goes. Now, I do not know details on logistics to come. I do not know exactly how we're going to conduct the exam. As soon as I know, I'll let you know. It's going to be some combination of, at least I'm thinking it's probably going to be some combination of a quiz on Canvas where you answer some questions. They're going to be very quickly timed. And then the other part will kind of be a take-home of problems similar to what you've seen in the homework. So basically what I'm trying to do is I'm trying to figure out, I'm not interested in your ability to look up problems in the solutions manual or online and give me those answers back. In fact, you'll get zeros for those. If you give me verbatim, right, do not copy solutions manuals or online resources. Do your work. Okay? It's an exam. Anyway, as I said, details on logistics to come. I'll explain kind of how the exam is going to work once I've kind of ironed out a few more details. Let's talk about content of the exam. So basically what I want you to do is I want you to study as if the exam was in class. If you're prepared for one of my regular in-class exams, you'll do just fine on whatever I design and put together or find as a good way to do this exam in an online format. So study as if you're going to take the exam in class. The exam will still be made up of problems similar to what you did in the homework and what we've done in class and examples. Okay? It will still consist of problems from chapter 5, 6, and 7 from your text. So that's what we're looking at. If we talk briefly about what's in those, of course, exam 2, as I've said several times, exam 2 comes down to the conservation laws, conservation of mass, conservation of energy, and conservation of momentum. So chapter 5, we can first start talking about the conservation of mass. And that's the idea that if you add up the rate of mass in, subtract the rate of mass out, everywhere you've got mass coming in, everywhere you've got mass going out, that's going to equal the change in the mass of your system with respect to time. Okay, let me see if I can pull this off. There we go. I'm learning as we go here. Okay? I'll grab from work an engineering pad, so it'll be a little bit easier to do this. Now, we know from previous work that the mass flow rate, of course, we can find in a number of ways. By the way, while you're watching these videos, I don't know how many of these we'll do, but as you're watching these, you should have pen and paper out, just like you were sitting in class, and take notes. Or whatever works for you, but I mean, just sitting there watching me do stuff on a video, I don't know how helpful that's going to be for you unless you find ways to actively engage in this. So I suggested a minimum take notes, but do what's going to work for you. Again, remember, we can find mass flow rate through density times volumetric flow rate, that's volume per time. We can find volumetric flow rate by taking the product of cross-sectional area and the average speed or velocity of the fluid particles moving through the conduit. That can also be found through area times speed divided by specific volume, the reciprocal of density, and that's also found through volumetric flow rate divided by specific volume, depending on what we have. So everywhere that mass comes into the system minus everywhere that mass goes out of the system, all of those mass flow rates, that sum equals the change in the mass of the system with respect to time. Now, often we have what this text calls steady flow. There are a lot of textbooks out there that call this steady state or equilibrium. That's where nothing is changing with respect to time. Everything's constant with respect to time. So if that's our situation, then what you've got is you've got your total mass flow rate in minus your total mass flow rate out is equal to 0. And of course, the one inlet and one outlet, that simply tells us that the mass flow rate in is equal to mass flow rate out. And we just call that m dot. There's no reason to differentiate between those. Okay, so that's conservation of mass, and it's not uncommon. We'll see one inlet and one outlet in a steady flow condition. Right, you can almost always make this assumption in our course. We're not going to deal with this guy's a differential equation. So, and we see the same thing with the conservation of energy. Right, so if we talk about conservation of energy, which of course is also known as the first law of thermodynamics, conservation of energy as applied to fluids. Now it starts with, or we could start with what we call the Bernoulli equation, which I think I've misspelled his name there. Sorry, Mr. Bernoulli. But that's pretty close, right? So the Bernoulli equation tells us that if you add all of essentially the mechanical energy of the fluid, that if you take pressure divided by density, add to it the kinetic energy of the fluid at a specific location, add to it the potential energy of the fluid at a specific location, that is equal to a constant. Meaning I can find all these at point 1, and then set that equal to all of these at point 2, and set them equal to all of these at point 3, at different points in the flow stream, as long as there's assumes no outside energy. So as long as there's no outside energy, as long as there's no turbines, there's no pumps, there's no frictional or mechanical loss, this holds up. We're saying the energy in is equal to the energy out is equal to the energy at any other point in the flow stream. Now, if we expand that to all forms of energy, what we get is we get what we call the general energy equation, which is just conservation of energy applied to fluids. And that says, well, if we work per unit mass, and so per unit mass, I apologize, my writing is probably even more sloppy than normal. I'm not used to doing a lecture like this on a notepad with pen and paper anymore. Anyway, if we look at per unit mass, that says that the energy per unit mass in, that's things like a pump, right here at the very bottom, that's things like a pump or compressor or anything else that's going to put work into the flow stream. So the work energy per unit mass in plus all of the energy of the mass coming in. So that would be like P1 over rho 1 plus, and there's this alpha term. We talked about the alpha term. We normally assume it's 1, but they might give you a value for alpha, or they might be asking for the value of alpha. So it is a term that does show up, plus the potential energy input, that's Gz at 1. That's going to equal all of the energy, all the mechanical energy that comes out. That's going to equal the work per unit mass coming out. That could be things like a turbine, maybe a paddle wheel, something like that, plus P2 over rho 2 plus alpha 2 V2 squared over 2 plus Gz2, and then plus the energy lost. Right? This is your thermal energy. That's the heat, the temperature increase. This is, again, there's different kinds of energy. This is not a thermo course, so we're not going to go into all of that, but there are different kinds of energy. And these, all of this is the mechanical energy in is equal to the mechanical energy out plus what we might call the thermal or mechanical energy lost. So again, the second law of thermodynamics, many of you have had thermo, or some of you are taking it right now. As we've mentioned, there's different kinds of energy. In all these mechanical energies, work, the baric or the pressure energy, the kinetic energy, the potential energy, it's easy to switch between these different forms. It's easy to turn all of these into thermal energy, heat and internal energy. It's really difficult to turn this thermal energy, this lost energy, back into one of these mechanical forms. So all these terms, the energy is pretty easy to go back and forth, and that's what Bernoulli was saying up here. Is these types of energies will change. On the screen there. Yeah. These types of energies will change back and forth pretty easily, and they all have to be conserved. They are all constant. But realistically, some of these energies are going to turn into this mechanical loss, and that's what we're going to look at in Chapter 8 for Exam 3 coming up, is how do we quantify this guy. For us, right now, this mechanical loss, we're either going to assume it's negligible, or it's going to be something that's given to us, or some way to find it, or it's what the problem's asking for. Right, those are the common things we can do with that. The rest of these are things that we are either given or we can figure out. Right, remember from Exam 1, we can find pressure within a column of fluid based on the elevation and the density. We can find the speed through the mass flow rate equation. Right? So we have some different tools for finding some of these different terms. Okay, now, how are we on time? Well, okay, not bad so far. Like I said, I'm fairly new at recording lectures like this, so hopefully I hope this is helpful. All right, what else? So I think then, so as we mentioned, this version is per unit mass. Okay. Now, as we've talked about, you can also work problems depending on what you're given in different dimension sets. You can work this per unit time easy enough. So if we work this equation per unit time, that means multiply by your mass flow rate equation, because up here all of these are per unit mass, and if I multiply by something that is mass per unit time, then I'm left with per unit time. And what that means is that the power input, big W dot in, this is energy per unit time, plus the m dot times P1 over rho 1 plus alpha 1 V1 squared over 2 plus GZ1. All of these quantities multiplied by the rate at which mass flows through gives you